Couple of announcements before we get into course material, just regarding homework and some logistical stuff. As a reminder, you have your first written homework due tonight. Scan that, upload that as a PDF to Wild Courses, doesn't involve Alex at all. Yesterday in Alex, you had an assignment due called Angles and Radians. That is now closed. If you did not do it though, or you didn't finish in time, don't worry. You will have one more chance before the exam happens. There is an assignment that opens the day of the exam and extends through that weekend called Second Chance Exam 1 topics. And so if you did not get those topics done in the first go, they will reopen and you will be able to complete them then for full credit. As well, you have your second knowledge check due over the weekend. Again, these are just for participation. However, I suggest you do as well as you can on these, because knowledge checks are where you go from having topics learned, which is what you did in the Angles and Radians module, to having topics mastered. And if you do not do well on these, or say you got some things correct on your initial knowledge check, so they were mastered, but then you get them wrong on knowledge check 2, you will actually lose mastery of those topics, which is unfortunate, but it does happen. You'll be able to regain back mastery later on later knowledge checks, but it is just in your best interest that you do as best as you can now, so you have less work to do later. So written homework due tonight, knowledge check over the weekend, and the next Alex module called Triangular and Circular Trigonometry should be open. That one's fairly large, but we've covered everything we need for it. It's just all of the stuff with evaluating sines, cosines, tangents, and then secants, cosecants, and cotangents, some in the context of the triangle and some in the context of circular coordinates. Are there any questions on that? Okay, well, if there's no questions, today all we are going to be focusing on is the graphs of sine and cosine. We may finish early today. Hopefully we will, because it's Friday, but that's all we're going to do today. So let me pull up the screen where we left off. Share content. Okie dokie. All right. So if you recall, at the end of class on Thursday, we started talking about the base graph of sine, and we did a little example of sketching sine. So just as a brief review, this is what the base graph of sine looks like, or what we're going to call the parent graph of sine. It is a wave. It repeats like this forever. We focused mainly on this guy right here, and that is called the principal interval. It is the only part of the graph we will need to focus on in order to graph transformations of sine. And I put a box around the principal interval because we'll be using that later. And this wave just comes from the behavior of a circle, because sine is the y-coordinate. So the y-coordinates in the unit circle start at 0. So the sine graph starts at 0. They increase until they get to pi halves, radians, which is right here, where they are at their highest value 1. They go back down until the y values are 0 again at pi. They go negative until they're -1 at 3 pi halves, and then back up to 0 for 2 pi. So the graph of sine makes sense. And then once we have this parent graph, we can pretty much graph any other function of sine without using a calculator and just using graph transformations. We started to get some intuition for what that looks like with this one, where we had y is 2 sine x minus 1. We recognized that that 2 in front stretched our graph by a factor of 2, or in the context of a wave, that's what we call the amplitude of a wave, which is the distance from the midpoint of the wave to the peaks of the wave. So it can be the top peak, bottom peak. Amplitude will always be a positive value because it is a distance. It doesn't have a sign, but the amplitude of the wave in this case is 2, so it stretched the entire wave by a factor of 2. And then we had this -1 at the end, which is what we call the vertical shift, and that just took our entire wave and popped it down by 1, popped the entire thing down by 1. So we use some intuition to graph this one. However, we want to get more of a system for how to graph these, something like a process we can go through every time we're given an equation, that we can just follow the steps and produce the graph. And that's what this next slide is. Steps to graphing sine or cosine. We don't have the parent graph of cosine yet, but this process actually happens to work for all trig functions. So let y equals a function This function could be sine, cosine, etc. Just fill in the blank, times bx plus c, or of bx plus c plus d. Let that be a trig function. The first step is just to identify the parent graph. And all that will be to do is to look at this guy right here, the function, and identify what it is. Again, parent graph would look something just like sine of x, which is what we just looked at. We'll also look at the parent for cosine of x. And we'll get to the other ones later, like tangent, cotangent, etc. But for now, we just focus on sine x and cosine x. Next is the step we did do on the last slide, which is to identify the amplitude and the vertical shift. These two are typically the easiest things to identify because you do not have to do any computation to find them. And these two things determine the y bounds of our wave. And I'll explain more what that means. But you just want to determine the amplitude, which is the stretch of the wave, and the vertical shift, which is whatever d is. And we will see more of that in examples in a minute, but just know that that's exactly what we did on the previous slide. Okay, next, then we're going to take the inside of the function bx plus c, so whatever's on the inside of our sine or cosine or whatever, and solve these inequalities for x. So we'll get an example of this again in a minute, but all you'd be doing there is, say, for example, I'll do one briefly. Say we have bx plus c being 5x plus 3. So say we have 0 is less than or equal to 5x plus 3 is less than or equal to 2 pi. All we would do to solve this is we can solve both of these inequalities simultaneously. We can start by subtracting 3 from all three sides, get -3 is less than or equal to 5x is less than or equal to 2 pi minus 3. And then we can just divide all three sides by 5 to get that -3/5 is less than or equal to x is less than or equal to 2 pi minus 3 over 5. Just a brief little review on how solving inequalities works. Hopefully you remember this from college algebra. If not, this will be good practice. But that is all step 3 is going to be. And what this is going to do, this is going to determine our x bounds. And I say the word bounds here very lightly. Essentially, what this is going to do is notice that the parent graph has a repeating interval of 0 to 2 pi. The principal interval is 0 to 2 pi, and we only care about the principal interval because once we are outside of that principal interval, we can just copy paste copies of that principal interval into the other intervals. So essentially what this is solving for down here is where the principal interval of this graph is going to be. And we will see that in action in a minute. But that is what this is doing. So step 2 gives us our y bounds. Step 3 determines where our principal interval is, so kind of gives us our x bounds. It'll determine where we draw this box here, this gray box, when we go to do our transformations. Okay, speaking of the box, step 4 is where we draw this box on the coordinate axis whose x bounds are the solutions to the inequality and whose y bounds are defined by the amplitude and vertical shift. So the amplitude will tell us how far we need to stretch it, and then the vertical shift will tell us, okay, how far up or down do we move this stretched box? So basically it frames graph in the correct location. And then step 5, we are to draw the parent graph as it looks in 0 to 2 pi in the box and extend it to the ends of the axes. So essentially we will be taking this parent right here and stretching or squishing or flipping however we need to fit in the box that we draw in step 4. And then we'll just make copies of that. Okay, so this might sound a little confusing and like a lot at first, so I think it would be easiest just to see what an example looks like. Okay, so we want to sketch the graph of y equals 3 times the sine of 2x plus pi. Let's walk through our steps. What's step 1 is to identify the parent graph. Well, it's sine. You just have to look for the trig function that is being used. That will be the parent graph. Okay, we have our parent. Beautiful. Step 2, we want to find the amplitude and the vertical shift. So in this case, the amplitude will always be positive, but it is always just the positive of the number that is out front. It is the positive of this multiple out here. 3 is already positive, so our amplitude is just 3. Easy enough. What about our vertical shift? Well, the vertical shift is just whatever is being added or subtracted on to the end. However, we have 3 sine of 2x plus pi, and then there's nothing else. We don't have a plus anything. We don't have a minus anything. So this graph actually has no vertical shift, which is nice for us. This actually means that we know where the y parts of our box are going to be. So I'll draw these in purple. Since our amplitude is 3, the normal sine wave would have a ceiling at 1 and -1, but that's not what we're working with. We need to stretch that by a factor of 3. So our y part of the box is going to be up here and down here. We don't know where the principal interval is or where the x bounds are going to be, but we know that they're going to intersect at 3 and 3 here. Okay, now let's do step 3, which is where we set up this inequality right here. 0 is less than or equal to bx plus c is less than or equal to 2 pi, and we just have to solve for x. So bx plus c in our case is 2x plus pi. It is what is in the argument here. So we can solve by going 0 is less than or equal to 2x plus pi is less than or equal to 2 pi. First, let's subtract pi from all 3 sides. And I'll just take this up here, keep working. So then we get that negative pi is less than or equal to 2x is less than or equal to 2 pi minus pi is pi. Lastly, we divide both sides by 2 and get that negative pi over 2 is less than or equal to x is less than or equal to pi over 2. So we divided all 3 sides by 2. So this is our interval. This is where our x bounds are going to be. This is going to be the x bounds of the principal interval. So I will draw these bounds in green. We have pi over 2 right here. And we have negative pi over 2 right here. And I accidentally didn't draw these far enough. So getting rid of this because we don't need it. This right here that we have is going to be our box. This is where we are going to squish or contort or stretch or whatever our parent graph of sine into so that we can see what this transformation of it looks like. Our multiple out front, our coefficient is positive, so we do not need to flip the sine function upside down. So we just need to draw it like it is in the parent, except fit into this box. So if I go back and look at the parent of sine, we can see that on the left-hand side of the box, it starts at 0 and ends at 0. And halfway through, it is also at 0. Quarter of the way through, we hit the amplitude, the peak, and then 3/4 of the way through, we hit the negative amplitude. Okay, so let's draw that in here. We know that it starts at 0, halfway through is 0, and then at the end is 0. Quarter of the way through, we hit the peak of our amplitude, that's right here. And then 3/4 of the way through, we hit our negative amplitude down here. And that creates this wave right here. Perfect, there's our principal interval. However, this is just a sketch. I have 2 axes here because I want to extend this to the entire graph and clean it up and make it look nicer. So I'll just copy the information I already have over here, like so. Whoop. There we go. But remember that this wave will repeat just for the entirety of the graph. So we can just kind of think about copy and pasting what our principal interval looks like throughout the entirety of the axes. So this is going to go back down and then up to look like this. And then this is going to go up and then down, and then down, and then up and down, just copying and pasting what our principal interval looks like until we reach the end of the axes. Because remember, it will go on like this forever because it's just going around. You can just think of it as going around the circle again and again and again. It's going to create the same wave. Are there any questions on how I did any of this? Okay. Well, if there's no questions, then let's talk about the other parent graph that I keep bringing up, which is the parent graph of cosine, or the base graph of cosine. So again, like sine, these x values represent an angle, what we have been calling theta. And the cosine of x is just whatever the value of cosine theta is on the unit circle. That's all this is. We just look at the x coordinate on our unit circle. That's all the cosine is. And then x is just the angle that's being put in. So on the unit circle, when x is 0, cosine is 1. When x is pi over 6, cosine is root 3 over 2, etc. I've already actually plotted the points of the principal interval just to make our lives a little bit easier here. So the principal interval of cosine is going to look something like this. If you'll notice, it definitely has its similarities to sine. It still has a very wavy shape, but whereas sine started at 0, cosine starts at 1. And then where here sine is actually crossing back over into 0, cosine is -1. So they definitely have a very key similarity that we will talk about soon, but they are a little different. So I will draw a box around this guy because this is our principal interval of cosine that we will be using when we do graph transformations. This is what we will be squishing and contorting into those boxes. And then just for sake of completion, to extend this to the rest of the axes, we can draw things in like so. Oh, come on. And the wave will look something like this. I did not draw on all the points, but that same thing like sine, the same shape will continue forever. We're just copying and pasting copies of the parent graph. Any questions? Okay, well then if there's no questions, let's do an example of a cosine transformation. I want to graph y equals -1/2 times the cosine of x minus 3 pi fourths minus 1. Again, first step, what's the parent graph? Well, it's the cosine of x. We just look for the trig function that is being used, and that will be our parent graph. Second step, we need to look for the amplitude and the vertical shift. Our amplitude here, even though there is a -1/2 in front, the amplitude is 1/2, not -1/2. Because amplitude is not describing a displacement. It is not, you cannot have negative amplitude. The amplitude is just describing how much it's being stretched or squished. However, that negative will be extraordinarily important because if you remember, like with quadratics, for example, whenever we had a negative out in front, it would flip our quadratic upside down. Same thing here. When we put the parent graph in our box that we draw, we will have to flip the parent upside down. So when we're talking about the amplitude of a wave, it will always be the positive of whatever that coefficient is. However, we do need to keep that negative in mind. Okay, so with that in mind, we can then look at our vertical shift. And this one is -1. We do leave the negative on for vertical shift because we are shifting down 1. So instead now, because we're shifting everything down 1, instead of 0 or the x-axis being our midline, -1 will be the midline of the wave. So with this in mind, we can now sketch in the y coordinates of our box. So the amplitude is 1/2, meaning instead of the graph having peaks at 1 and -1, it would have peaks at 0.5 and -0.05. However, that's not quite complete either because this is just the amplitude. Now we need to take into account the vertical shift. We need to move both of these lines down by 1, down because it's negative, in order to have the correct y, max y, and minimum y coordinates of our graph. So 0.5 minus 1 is -0.05, so I can leave that line alone. But -0.05 minus 1 is -1.5. Does this make sense? Are there any questions on why those are our y coordinates? Okay, now let's talk about the x coordinates. Step 3, we want to take this argument and solve the inequality 0 is less than or equal to x minus 3 pi fourths is less than or equal to 2 pi. We want to solve for x just to find out where our principal interval is, because when it's sine x, our principal interval is 0 to 2 pi. However, we're changing that because the argument is different, so we need to solve for what that looks like. Okay, so we actually, all we need to do here is add 3 pi fourths to all three sides, because there's no stretch or squish on the x, so all we need to do is add that. So we get that 3 pi over 4 is less than or equal to x is less than or equal to 2 pi, which is equal to 8 pi fourths, plus 3 pi fourths is 11 pi fourths. So instead of being from 0 to 2 pi, our principal interval is going to be from 3 pi fourths to 11 pi fourths. So we have 3 pi fourths right here and 11 pi fourths right here. I once again did not draw the y box to be large enough. However, getting rid of that over there, that is going to be where we are going to place our principal interval. Okay, so remember the graph of cosine looks like this. It's kind of a U shape. It starts at 1, hits 0 at a quarter of the way through. Halfway through, we're at -1. 3/4 of the way through, we're at 0 again, and then back up to 1. However, if you recall, we have this negative out in front, so we just need to take this U shape and flip it upside down, so then it's more of like a hill. So because this starts at 1 here, we're negating everything, so that becomes -1. And then we have a -1 over here where we're ending. Halfway through 3 pi fourths and 11 pi fourths, the midpoint of that happens to be 7 pi fourths. You can check this mathematically, but we know that that's going to be there. And then quarter of the way through, we would normally hit 0, aka our midline. But as we talked about here, our midline is -1. We can even draw a dotted line here if it helps us think about it that way. Think of it as where the parent intersected the x-axis. We're going to intersect the midline. So we intersect the midline here and here, just from looking at our parent graph. So we know that it's going to look something like this, drawing it in the shape of the parent just right there. Now, all we have to do is take copies of this parent and copy it to the rest of the axes, and then we have our complete graph. So I'm just going to copy this over really quickly, copy the information we already have. Looks like that. Okay, then we just got to keep extending it. And that is as far as we can extend it on these axes, but it looks something like this. Any questions on how I got that answer? Okay, so I've been throwing around words like amplitude, period, phase shift, etc. Let's talk about what those actually mean and where they appear in our equation. So in general, we are going to be looking at equations of the form y equals a sine of bx plus c plus d, or y equals a cosine of bx plus c plus d. The a, b, c, and d are just numbers. They're not variables. You will always be given a number for them or asked to find the number. That will be coming up soon. But a, b, c, and d are just numbers. And from those four numbers, I want to know where the amplitude, period, and phase shift come in. The easiest one to look at right away is the amplitude, because we can just pluck it off the front. However, I've talked about how the amplitude is always the positive of what's on the front. So the amplitude is actually what we call the absolute value of A. And if you remember from college algebra or another class you may have taken, the absolute value sign just takes the positive of whatever's in the argument. So if we want the absolute value of -12, it's 12. That's it. If the number's already positive, we don't need to do anything to it. So that will be your amplitude. When you are graphing, you do need to keep in mind if there is a negative or not, because if there is a negative, you will need to flip your graph upside down. However, the amplitude as defined is just the absolute value of A. The period, before I write the formula down, intuitively, the period is the amount of time, I'm putting time in quotes, it takes to repeat itself. So like on our last graph up here, the period was still 2 pi because it took 2 pi radians in order for the graph to repeat itself. However, on our example with sine, the period was much smaller. The period was actually pi because the principal interval only had length pi. So every pi radians, this graph repeated itself. So how do we find the period? Well, my gut reaction would be, oh, it's B, but it's not B. B is actually what we use to find the period. It turns out that the period is actually 2 pi divided by B, which makes sense. That comes in when we're solving the inequality. Like for the sine example up here, B was 2, and we had to divide all of the sides by 2 in order to get x by itself. And when we divided everything by 2, we cut that period of 2 pi by half. So that's where that formula comes from, is we're just dividing it by B, because if the period is large, that will decrease the period, because the original period is 2 pi. So if B is large, dividing it will make the period smaller. But if B is like 1/2 or something, when we divide by a fraction, the period would get even bigger. So that's where that comes from. Whenever you are asked to find the period or given the period and need to find B, for example, hint, hint, that may or may not happen, you just need to use this formula right here. And then the phase shift. The phase shift, that word is when we talk about moving the x's. Period was talking about squishing or stretching things. The phase shift is talking about shifting the x's, kind of like, I don't know why this isn't written in here, how vertical shift is just whatever d is. The phase shift is going to be whatever the vertical shift is. And again, as tempting as it is to say that it's C, it's not just quite C. So intuitively, the phase shift is just the amount of horizontal shift our box, i.e. the principal interval, had to undergo. And the way we find this may not seem intuitive at first, but it may make sense more when you work with it. The phase shift is equal to -c divided by b. And again, this comes in when we're solving this inequality of 0 to 2 pi. We subtract c from both sides. So that's where the -c comes in. We have to subtract c from everything in order to, get rid of c from where we want to solve for x. And then we divide by b. So that is exactly where the phase shift comes in, is when we are doing that. So yeah, it is negative c divided by b. And just recall that that is found in solving this inequality. Are there any questions on these definitions? Okay. So just to test our little knowledge with this vocabulary, let's look at a graph. And we don't have to graph this one, but let's just see if we can identify the amplitude, period, and the phase shift. I always like to start with amplitude because I think it's the easiest. It doesn't require any computation. It's just kind of look at it, and if you know what you're looking at, there's the answer. So we have -3 minus 2/3 sine of -pi² x minus pi3. The amplitude, okay, this is what's in the front, but it's not a coefficient, so it's not -3. We're looking at this guy right here. We have a coefficient of -2 pi3. However, the amplitude is the absolute value of -2/3, which is just 2/3. So our amplitude is 2/3. Next, I'm going to look at the period. And the period, if you recall from this slide, all we need to do to solve for the period is just 2 pi divided by whatever b is. So we have that the period is equal to 2 pi divided by b. B is the coefficient on the x guy here, and so that is -pi². But we need to put it in absolute value. Oh, I forgot to mention, this will almost never come up. This is like the one time it's going to come up, but it's actually, the period is actually 2 pi divided by the absolute value of b. I didn't mention that because it almost never ever comes up, because there are much cleaner ways to write things than having a negative period, and you'll see why. However, you do need to take the absolute value in the denominator. I should have mentioned that. Okay. So the period then is 2 pi over the absolute value of -pi², which is 2 pi over 1. Then doing fraction division, we invert and multiply, times 2 over pi, which is 4 pi over pi. Pi's cancel, so we're just left with a period of 4. Again, a period, if we left the negative sign there, we would have a period of -4, which doesn't really make sense. That's why we don't ever even really think about that absolute value in the denominator, because the period, like we talked about, is the amount of time the graph takes to repeat itself. And why would it take -4 radians to repeat itself? It just doesn't make sense. So period will always be positive as well. And then once we have this, we can now solve for the phase shift. The phase shift, if you remember from the formula, is just -c divided by b. No absolute values needed here, because the phase shift, we are talking about shifting in a positive or negative direction. Sign with phase shift actually matters. So it is just -c. C is pi3, so it is positive pi3 because it's negative pi3 over b, which is -pi². Again, doing some fancy handy dandy fraction division, we invert and multiply, get -2 over pi. The pi's cancel, and we are just left with -2/3. And then I didn't ask for this one, but the vertical shift would just be -3, because it is what we are adding or subtracting. It's how much we're shifting the graph up or down. It was put in the beginning this time. It can be put anywhere, but yeah, that's our vertical shift, is you just pluck d out of the equation. Any questions on this vocabulary? Okay, so then if there are no questions, let's try using these to try a little bit of a different skill, going backwards a little bit. Instead of being given an equation and having to produce the graph, what if I just give you a graph and ask you to produce the equation? Okay, so first I want to write an equation in the form y equals a sine bx or y equals a cosine bx for the graph below. This right here is super handy dandy information, because what it tells us is that there is no phase shift because there is no C. There's no phase shift at all. We will not be having to shift the graph around. And in addition, there is no vertical shift. We know that the amplitude may be stretched or compressed, so the amplitude may change and there may be a different period. However, we have no phase shift. Okay, so let's start again. I like amplitude because amplitude is usually the easiest to identify. So we're still starting at 0, which is great, and ending at 0. I will draw the box around our principal interval, which we know starts right on the y-axis because there's no phase shift. Having no phase shift tells us where to draw our box because we know that it starts right at 0. We didn't move it left, we didn't move it right, so that's what our box is going to look like. Okay, so our midline, because there's no vertical shift, is still 0. Notice that instead of going up to 1 and then down to -1, we only go up to 0.75 and down to -0.75. So our amplitude is 0.75 because we are multiplying all of the values in the sine graph by a factor of 0.75. Also notice though, that when we plug it into our sine equation, it will actually be -0.75 because the parent graph of sine, if we look right here, goes up first, but here the parent graph of sine, not the parent graph, this graph of sine goes down. So our actual value A in this equation is -0.75. Cool, we're halfway there. All right, now let's consider B. So to get B, we first need to identify the period. We can get the period just by looking at this graph because we know where the principal interval is. That is, we know how long it takes for the sine graph to complete one complete cycle. So if we look at the graph, we can immediately see that the period, it goes 0 and then 2 pi thirds. So the period is 2 pi thirds because this one wave ends at x equals 2 pi thirds. So it took 2 pi thirds radians in order to complete the cycle. Now, this is not B, remember, we need to use this value in order to solve for B. And to get that, we need to take our period, which we just found, and say that it equals to 2 pi over B, and then we solve for B. So 2 pi thirds is equal to 2 pi over B. We need to do some cross multiplication here. We'll get that 2 pi B equals 6 pi. And that was just doing some cross multiplication where I did kind of one of these things. I don't know if you remember that from algebra. There's other ways to solve it. You could multiply both sides by B and then multiply both sides by 3. Same idea. But dividing both sides by 2 pi, we get that B is equal to 3. So that gives us our equation right there. Because we know it's in this form, there's no vertical shift, there's no phase shift. We know that the graph is y equals a, which is -0.75, times our parent, which is sine, because it looks like the sine function. If it were cosine, we would have to be starting at either our negative amplitude or our positive amplitude, but it's not, which we know because there's no phase shift. So it's -0.75 times the sine of B, which is 3 times x. Any questions on how we came up with this one? Okay, so now let's do that again, except this time I forgot to write this in and I should have, but these are either going to be of the form a sine of bx plus d or a cosine of bx plus d. So I'm still not allowing for any phase shift at all. I know that my box of my principal interval is going to start right here. However, there is now the potential of a vertical shift, which we can see definitely happened because our graph hits a maximum of 5, but it doesn't hit a maximum of -5 or a minimum of -5. It hits a minimum of -3. So we know there was some vertical shifting going around, which also makes sense because this guy starts at a very weird point. It does not start at 0 or the maximum or minimum. It starts at 1. You could think about if we shifted this back down 1, that our minimum would be at -4 and our maximum would be at +4. So the midline of this graph is right here. We can see that that kind of looks correct visually too. So that means that this graph has a vertical shift of +1, which means that D equals 1 because we're just going to have to add a 1 onto the end to make this all make sense. And we were able to do this by identifying right away that there was no phase shift. We know we didn't have to try to move it left or right in order for us to start on a 0 or at one of the negative or positive points. Knowing that there was no phase shift immediately told us that we had a vertical shift. Okay, vertical shift identified. Let's work with the next easiest one, which is the amplitude. Amplitude is just the distance from the midline to the highest/lowest points. Here, let's just look at the high one. The high point is at 5, the midline is at 1, 5 minus 1, the difference between the two, the distance between the two is 4. So our amplitude A is 4. However, notice that again, we are working with sine because of the shape of the parent, and it's negative instead of going up. Oh, wrong way. Instead of going up at the start, we're going down. So A is going to be -4. Let me finish drawing this box real quick, just to give us a good visual aid. And I did forget to mention, but I've been kind of doing this subconsciously, but you should be doing this check every time. Both of these in the box look like the graph of sine. And the reason that we are forced into using sine here is because we're told that there's no phase shift. Notice if I scooched some of these boxes over, like for example, if I decided to make my box here on this one, we're looking at the parent of cosine instead. That will come up later, where we can actually use both sine and cosine to describe the same graph. But because we're looking at the instance of no phase shift, we don't have to worry about that. But you should be doing the check right away initially. Am I looking at a parent of sine, or am I looking at a transformation of the parent of cosine? Should always be doing that check. These just happen to be both sine by construction of the problem, but I digress. Anyways, okay. So lastly, we have our vertical shift. Back to the pen. We have our amplitude. All that is left is B, which we find using our period. So the period of this graph, we start at 0, and then we go through a full cycle at 3. So the period is 3. Again, we just need to solve that equation where we know that the period, which is 3, is equal to 2 pi divided by B. Multiply both sides by B, we get that 3B is equal to 2 pi. Divide both sides by 3 to get B by itself. We get that B is equal to 2 pi thirds. And so our final answer is that I'm just going to erase this right here to make room. We get that Y is equal to negative A, so -4. We identified that our parent is sine of B, 2 pi thirds x, and then plus D, so plus 1. So this got a little more complicated when we added in the vertical shift. Are there any questions on how we got here? Okay. So just as a brief note, I mentioned that we may be able to create 2 different equations, sine or cosine, from the exact same graph. And it turns out that for any graph of sine or cosine, we will be able to create a sine and a cosine version of it. And the reason for this is sine and cosine, these parent graphs, if you notice, have the exact same shape. They just are shifted over a little bit. So notice these graphs have the same shape. It's exactly the same. They have the same amplitude. They have the same period, etc. The only thing that is different between them is the phase shift. They're just shifted over. Okay, let's say that we're looking at sine, or even, no, let's look at cosine. So cosine starts at 1, goes down to 0, down to -1, etc. Notice that if we shift cosine over to the right by a factor of pi, we get the sine graph. Similarly, if we shift the sine over to the right or over to the left by a factor of pi, if you think of taking this part of the graph, moving it over to here, we'll take this point, move, or wait, is it that point? Yeah, take this point, move it over here, take this point, move it over here. We get the parent graph of cosine. And all I did there, okay, this point was at pi halves, I moved it over to 0. This point was at pi, I moved it over to pi halves. This point was at 3 pi halves, I moved over to pi. They're just shifted over by a factor of pi halves. That's all they're doing. They're the exact same graph if we just shift them over. Because I can even draw this in completely. And you can see that if all of these points we just shift over by that factor of pi halves, we can create the parent of the other graph. So that means that we could actually write the parent for cosine in terms of sine and the parent of sine in terms of cosine. Are there any questions on that? The main idea here and the main takeaway is that all graphs can be described, and by all graphs, I'll put sine, cosine graphs. All of these graphs of sine and cosine can be described by both sine and cosine functions. That is the key takeaway here. Let's see an example of that because this sounds kind of confusing. Okay, so write an equation of the form y equals a cosine bx to describe the graph below. It's the same process we've been doing. Let's just do it again, get some more practice with it. Okay, so I want this to be in the form of cosine. So I see it's cosine, if you recall, looks like this. We need to start at one of our peaks, go down to 0, hit the other peak halfway through, go through 0 3/4 of the way through, and then hit a peak at the end. This would describe a graph of negative cosine, but that's still sufficient. That's what we're looking for. And it really nicely lines my box up with the y-axis, which I always love when that happens because that means there will be no phase shift. So I'm going to choose this to be my principal interval that I will be working with. All I need is that bit of information in order to determine what the entire graph looks like. So having that in mind, we can see right away our midline is still the x-axis because there's no vertical shift. And we go up 2 and we go down to -2. So our amplitude is just 2. However, like I mentioned, it is the parent of cosine, but flipped upside down. So our value a in the equation will be -2 because we need to take that flip into account. Now we can solve for our b value using our period. Our period in this case, we're going from 0 to 3 pi. So the period is 3 pi. But then plugging it into that equation for b, we get that 3 pi is equal to 2 pi over b. multiply both sides by b, we get 3 pi b equals 2 pi. Dividing both sides by 3 pi, we land at the answer that b equals 2/3. So that is our b value in the equation. And then we're actually just done. We know there's no vertical shift. We know that there is no phase shift because we're starting right on that y-axis, just like we wanted to. So our final answer is just y equals a, which is -2, times the cosine of 2/3 x. Beautiful. Any questions? Okay. What if I wanted to make this a little harder for us? What if now we're not allowed to use cosine as our parent? I want an equation in the form of sine. And this little c here should be an indicator that there's going to be a phase shift now. There's still no vertical shift because if you'll notice, it is the exact same graph, except now I don't want to use cosine. I'm not allowed to use cosine. That would be too easy. So we need to construct a parent of this in the form of sine. So let me find my principal interval. This seems like a nice place to start because sine on both sides of the interval, we need to start at 0, go up to the peak quarter of the way through, 0 again halfway through, another peak 3/4 of the way through, and then end there. So this would be our interval that we're going to work with, except now we do have a phase shift, and that will be that space there. It's the space that we shifted over. It's the distance from the y-axis. That is what the phase shift is, and you'll see that in computation in a second. But first, let's just go through our process again. Amplitude actually didn't change. The amplitude is still 2 because the x-axis is still our midline, and we're going up 2 from that midline to get to the top of the graph, and then 2 down to get to the bottom of the graph. So our amplitude is still just 2. Nice. Notice in this case, though, we are looking at the positive version of the parent of sine. It's not flipped upside down. We go up first. We don't go down. It does maintain this shape here. So we don't need to negate this 2. So our a value is just 2. Okay. Now what? Let's again look at our period. Notice that we are going from 15 pi fourths back to 3 pi fourths, so our period would be 15 pi fourths minus 3 pi fourths, which is just 12 pi fourths, which is just 3, because 12 divided by 4 is 3. It's 3 pi. Notice that's actually still the period over here. We take the same amount to go around that cycle. It doesn't take any longer because it's the same graph. We're not squishing it anymore. We're not stretching it anymore. It takes the same amount of time or the same amount of radians in order to complete our period. It's just in a different spot now. So what that means is our b value is actually going to stay the same at 2/3 because the amount of stretch or squish of the graph doesn't change whether we're using sine or cosine, but it's just in a different place. That's it. So our period is still exactly the same. However, what is going to be different is the phase shift. Because we started on the y-axis when we used cosine, there was no phase shift at all. We started at 0. We didn't move over at all. The distance between where our interval started and 0 is 0. It was great. It was nice. However, we don't have that anymore. We have this guy here. Notice that we are shifted over from the y-axis 3 pi fourths. In other words, the starting point of our sine function is 3 pi fourths over from where the principal is. So our phase shift is 3 pi fourths. Now remember, as tempting as it is to just slap this value in for c, we can't do that. This is not c. We have the equation all the way back up here that our phase shift is actually equal to -c over b. So we can use this in order to solve for c. So going back down here, we can say that 3 pi fourths is equal to negative c over b, and b is 2/3. Doing some arithmetic here, this gets us to 3 pi/4. We need to multiply both sides by 3/2 to get that 2/3 out of the denominator, and that is negative c. So 9 pi/8 is negative c. Therefore, c is equal to negative 9 pi/8. Any questions on that calculation? Okay, we have A, we have B, we have C. Beautiful. Now we just get to plug it into our form that we know it is because there is no vertical shift. So our equation of this graph will be y is equal to 2 times the sine of b is 2/3 x minus c, which is 9, or plus c, but c is negative 9 pi/8. And that is our answer. And recall the equation we got on the last slide, which is y equals negative 2 cosine 2/3 x, describes the exact same graph. We just had to shift it over. Are there any questions on how I did this and why these two describe the same graph? I may ask you in the future. I will give you a graph and say, give me an equation for this graph, both a sine and a cosine equation. You will always be able to do that. There is no graph of sine or cosine where you could not find a form that either use sine or cosine. One will usually be more difficult than the other, especially when one includes a phase shift and one does not. But if you are able to identify where your principal interval is, draw your box, find the amplitude, look at it, tell what the period is from the box, solve for B that way, look at it, extract the phase shift from where your box is, solve for C, and then look at a vertical shift, solve for D. The first thing you should always check for is a vertical shift, so you need to see if you need to move your midline. But if you're able to extract all of that information from the graph, how we have just done, you should be golden. Are there any questions on this process in general? Okay, so there's a couple kinds of word problems we can do. I will do one, maybe two really quickly. And these are just about extracting information and using what we know and doing an oh, never mind. We have one more problem. We will not be doing word problems today. We'll be doing one more example of graphing. I forgot about this one. Let's just do one more example of one that's a bit trickier, just to solidify our practice, and then I will let you guys go for the day. The word problems will actually be a good place to start for next time. Okay, so we want to write the equation of sine or cosine to describe this graph here. I'm not going to force us to do either this time because we now know that we can use both, but looking at this right off the bat, I kind of want to use cosine because cosine fits really nicely if we use these as the two starting and ending points of our interval. We nicely have a positive variation of the parent graph of cosine. So using this information, I will just draw my box. Cool. That's the hard part. We know where the box is. We have a peak at 4 and a minimum at -4. So that means we know that there will be no vertical shift. Our midline is still 0. There is a distance of 4 here and a distance of 4 here. So our amplitude is +4. So our A value is 4. And I'll just write A, and we've decided we're going to use cosine because that is the shape we have that fit the most nicely. Cool, we already have A. We're doing well. Okay, now looking at this box, we know we start at this point and end at this point. Now these aren't marked, but if I look at my units, it took 3 squares to get to pi/4, 3 more to get to pi/2, 3 more to get to 3 pi/4, and then 3 more to get to pi. So these units, each little unit on our grid here is 1/12 of a pi because it took us 12 units to get to pi. So each of these little units is a 1/12 of pi, and it took us this starting point right here is 2/12 of pi. So this point is pi/6. And here we have 12 pi/12, 13 pi/12, and then 14 pi twelfths. So this point right here is 14 pi over 12. So to get our period, we just take the difference of these two to find the length of this segment. We have 14 pi twelfths pi twelfths minus 2 pi twelfths, which I simplified to pi over 6. 14 minus 2 is 12 pi twelfths, which is just pi. So our period is pi. That's nice. Okay. Now that we have this period, we can use it to solve for b. We know that pi, our period, is equal to 2 pi divided by b. Multiplying both sides by b, pi b equals 2 pi. Divide by pi to get b by itself. We get that b is pi. This is one of the very rare cases. Oh, no, b is not pi. B is 2. Oopsies. 2. B is 2. Thank you, brain. Okay. Yeah, because 2 pi divided by pi, the pi's just cancel. All right, so we have that our a value is 4 and our b value is 2. We are almost done. Nice. Now that we have this b value, we can use it to solve for c. But first, to do that, we need the phase shift. So looking at this graph, here's the y-axis, here's this. All this distance right here is the phase shift, if you remember. Just the distance, we had to scooch the parent away from the y-axis in order to get this. The distance our box is scooched away from the y-axis. And right here, because this is 0 and this value is pi 6, our phase shift is just pi over 6. And now we can use this to solve for c. We know that pi over 6 is equal to negative c divided by b, which is 2. Multiplying both sides by 2, we get that pi thirds, in other words, 2 pi sixths, is equal to negative c. And therefore, c is equal to negative pi thirds. We're done. We just need to plug this into our equation. So substituting everything in to this form up here, we get that y is equal to a is 4, which we don't need to negate because we have a positive variation of the cosine parent. So it's 4 times the cosine of b, which is 2x plus c, so minus pi thirds. All right, these are all the examples we're going to do for extracting equations for sine and cosine from graphs and producing a graph given an equation. Are there any questions on this topic at all? Okay, you will get lots of practice with these in ALEKS and on the next homework. If you have any questions on these, I know these can be very difficult at first, especially when you're just getting comfortable with it. So please shoot me an email or come to office hours. And I will also stick around after class for a couple minutes today, if that would help anybody. But that is all we're going to cover for today. Next time, we are going to get into doing a couple examples of applications with this. And then we will start talking about graphs of other trig functions like tangent and cotangent. Okay. That is all I have for today. I will let you guys go a few minutes early. Don't forget your ALEKS knowledge check this weekend and your written homework due tonight. Otherwise, have a fabulous weekend, and I will see all of you on Monday.